1 plus R2 plus by using that equation R12 equals to R1 R2 upon R1 plus R2 plus R1 R2 by R3. The figure is such like that. The star connection, this one is a neutral point. Now the star is this is the configuration. First of all, for example, this one is our R1, R2 and R3. So here it is suppose 20 ohm, it is 30 ohm and it is somehow 50 ohm. So we have to just find out its equivalent delta connection. So for example, this one is R12, this one is R23 and this one is R31. We are just giving R1, R2 and R3 and we have to just convert that system or that circuit into delta connection. This is your start connection and this is your delta connection. So we have to just find out R12, R31 and R23. So now starting with that, first of all the R12 is R1. If you have to convert star to delta, then whatever the suppose R12, so first of all taking individual resistance summation like R1 plus R2, then after taking the parallel configuration R1 R2 upon whose the resistance is remaining, that is R3. So now putting the value of R1, R2 and R3, we are getting that R12 equals to 20. The value of R1 is 20 ohm. The value of R2 is 30 ohm. So by 20 plus 30 and by taking the 20-30 multiplication divided by R3 resistor, that is 50, we are getting that R12 equals to 62 ohm. So this is the resistance between the phase 1 and the phase 2. Similarly, R23 equals to R2 plus R3 plus R2 R3 divided by remaining resistance, that is R1. So by taking the value of that all these three resistor, we are getting that R23 equals to 30, that is the value of R2, 50, that is the value of R3, plus 30 into 50, and by taking the division of R1, that is 20 ohm. So by we are getting that R23 equals to 155 ohm, which is the resistance between the phase 2 and the phase 3. Now the last one, that is the phase 3 and the phase 1, that is the resistance is known as the R31, or you can say that R13. This is first of all the equation is right like that, R3 plus R1 plus by taking the parallel configuration like that, R3 R1 divided by R2. So by putting the value of R1, R2 and R3, we are getting that R31 equals to 50 plus 20 plus 50 20, these are in multiplication, divided by 30. So we get the value of R31, that is 103.3 ohm. So here we are just finding that equivalent capacitance of star R1, R2 and R3 respectively R12, R23 and R31 in delta connection. Now this is one important video for the delta to star and star to delta transformation.
Sometimes it is very much required to transform a delta connection in electric network to star for simplifying it. For delta to star transformation, we will first consider 3 points A, B and C on a network where a delta is connected as shown. Here, resistor R1 is connected across points A and C, resistor R3 is connected across points C and B, and resistor R2 is connected across points B and A. Now, suppose an equivalent star is connected in place of the delta, and we have to calculate the resistance of each arm of the star in terms of each resistance of that delta. Let arm of resistance Ra of the equivalent star is connected with point A, arm of resistance Rb of the equivalent star is connected with point B, and arm of resistance Rc is connected with point C. Now think about the resistance value of the delta across points B and C, and as you see from the diagram, there are two parallel resistive paths across B and C. One path is through resistor R3 and another path is through series combination of R2 and R1. Hence, the equivalent resistance between these points will be parallel combination of R3 and R2 plus R1, and this is equal to R3 into R2 plus R1 divided by R1 plus R2 plus R3. Now think about the resistance value of the star across same points B and C. As you see from the diagram, there are two resistors RB and RC across the points B and C. Hence, the equivalent resistance between these points will be series combination of RB and RC, and this is equal to RB plus RC. Here RA will not come into our calculation as it is just open circuited. Since the two systems are identical, resistances measured between points B and C in both of the systems must be equal. So, RB plus RC is equal to R3 into R2 plus R1 divided by R1 plus R2 plus R3, and say this is equation 1. Similarly, if we think about the equivalent resistance of delta and star respectively in between points C and A, we can prove that RC plus RA is equal to R1 into R3 plus R2 divided by R1 plus R2 plus R3, and say this is equation 2. When we think about points A and B in the diagram, we can similarly prove that RA plus RB is equal to R2 into R1 plus R3 divided by R1 plus R2 plus R3, and say this is equation 3. Now if we add equations 1, 2 and 3, we shall get 2 into RA plus RB plus RC is equal to 2 into R1 into R3 plus R2 into R3 plus R1 into R2 divided by R1 plus R2 plus R3, or RA plus RB plus RC is equal to R1 into R3 plus R2 into R3 plus R1 into R2 divided by R1 plus R2 plus R3, and say this is equation 4. Now if we subtract equations 1, 2 and 3 from equation 4, we will have respectively RA equals R1 into R2 divided by R1 plus R2 plus R3, RB equals R2 into R3 divided by R1 plus R2 plus R3, and RC equals R3 into R1 divided by R1 plus R2 plus R3. This is resistance of each arm of the star in.
This is again very important video for finding the transformation between the delta to star and the star to delta. Here it is just given the delta to star conversion, because we already proven with our example star to delta transformation. So students, many time in GTU exams again the question is asked like that. You are just given some of the quantities, some of the parameters, and you have to just convert or to transform that parameter into star to delta or delta to star conversion. So this is again very helpful equation for finding or for converting all the two configuration. Now just move towards the next question. The question is question 3b. Derive the expression for the parallel plate capacitor with uniform dielectric medium. Now in that paper, this question we can say that it's a repeat question, or it is somehow twisted for the our question 3a, which is an optional question. So you can again prove for the parallel plate capacitance in that one, and it contains almost the 8 marks. Just go through the first quick overview. This is the parallel plate capacitor where the voltages are same for all this capacitor, but the charge is the summation for all these 3 capacitors or 4 capacitors or the n number of capacitors. As we already prove, go through that one. We are not just discuss about the parallel plate capacitor. We just go through the quick overview of that. C is the charge of the capacitance of the capacitor, that is given with the quantity C equals to Q by V. Q is the charge of the capacitor, which is the product of the capacitance and the applied voltage, that is C into V. Q equals to Q1 Q plus Q2 plus Q3, it is the summation of all this charge storage in the capacitor. And the last one is the find out the equivalent capacitance, that is CE equals to sigma I equals to 1 to n into Ci, where n is the number of capacitors. This is the summary which we already proven. Now this is the capacitor in series, as we already talk about that, so just go through quick overview of that. And this is the summary of the capacitance. Yes. Now the next question, it is also an important question asked in many times. Derive the relation between the line voltage and the phase voltage in the balanced three-phase star connected system. Now again, this is a star connected system. Friends, the polyphase circuit or the three-phase circuit can be connected in two configurations. Either it can be converted into the star configuration or it is connected in a delta connection. Remember one thing most important, then all this parameter line voltage, line current, phase voltage and phase current are differ in a different configuration. They are differ in a star connection, they are differ in a delta connection. We have to just go through whatever the configuration in a star connected system. First of all, just go through all these terms, what exactly the line voltage, what exactly the line current, phase voltage and the phase current. This is the figure given to you. First one is a star connection, the second one is a delta connection. Now the terms, the first one is the phase. What exactly the phase is in a star connection or in a delta connection? It is describing by one element of any device in a load, line or in a source. Whatever the elements which are connected with the load, which are connected with the line or which are connected with the source, it is simply a branch of the circuit. So whatever the branch is divided into your circuit, this is called as a phase. So if we are talking about the three-phase circuit, it means that that circuit carries the three different branches. The second one is the line. It refers to the transmission line. The line is very important term because whenever you are giving the three-phase supply, that is 440 voltages, then this is passing through your elements via this transmission line, and this is commonly or shortly known as a line. It is simply the wires or the bunch of the wire that can carry the current from one source to the another part of the circuit. It may be modeled as a small impedance, actually the three of them, any one of them you can using, or even just of the connecting the lines. So the three-phase circuit contains the three lines or three phases individually. The neutral is the point, or you can say that it's a common point for all these lines. So all these lines are connected with the common point. That point is known as a neutral, which contains the zero level because it's a neutral point. So it doesn't have the positive value or it doesn't have any negative value. Now just phase voltage and the phase current. We are just go through the phase. Now whatever the value for the phase voltage and whatever the value for the phase current, the phase voltage and the phase current across the any single branch or the three of branch of the circuit. Now this is the definition, depends on the configuration, whether you are preferring the Y connection or the star connection or you are preferring the delta connection. Then next one is the line current, the current flowing through in each individual line. That is, if you are current flowing through the R phase, Y phase or the B phase, or you can say that it's a current flowing from the A, B and C. There is no matter if you are talking about the RYB phase or ABC phase or the 1, 2, 3 phase. So individual current passing through the line is known as the line current. Then the line voltage. The voltage between any two lines are known as a line voltage. So if we are taking the configuration such like that, if we are taking the connection delta, so this is the delta connection. If this is individually phase and this is given the supply, a three-phase supply. So this is the three lines line 1, line 2 and line 3, and here you are giving the supply. So what is the line? This is called line current IA passing from that. Suppose this one is A, B and C, these are the phase IA. Now here your current is IB and here your current is IC. So this is the line current. Now whatever the line voltage between A and B, this is called VAB. So this is the line voltage between A and B. Now between B and C, because this is your A phase, B and your C phase, so here you can find that VBC, the line voltage between B and C, and the voltage between A and C, that is VAC. So this is called the line voltage. And if you want to find out that the phase voltage, then this one is your phase VA, here your VC, and here your voltage, that is VB. So this is called the phase voltage, and whatever the current passing from that phase is known as a phase current. This is our delta connection, and we just go through the definition of the line voltage, line current, phase voltage and the phase current for the star and delta. Remember one thing, this is not the fixed configuration. This one is depends on whatever the configuration you follow. Either you can follow the delta configuration or you follow just star configuration. Now the three phase, as we already talked, that the three phase connection is divided into two main parts, the star connection or the delta connection. This is called the star connection, where A, B and C, these are the three phase. This is already, star connection is also known as the Y connection. You can see over here the star connection is from connecting any one starting of the one phase is connected with the end terminal of the individual phase, and all these phases are connected with one common point which is known as a neutral point. Now the line voltage, as we already known for the delta connection, so here the line voltage, phase voltage, line current and the phase current. Now just quickly go through the relation between the line voltage, line current, phase voltage and phase current for the star connection. First of all, prove the line voltage and the phase voltage. In star connection, your line voltage is greater than your phase voltage, and this one is with the root 3 times it is greater than with the phase voltage. So our equation becomes that VL equals to root 3 into VPH, where VL is the line voltage and VPH is the phase voltage. Or you can write like that, your VPH equals to root 3 1 by root 3 into VL. So this is the relation between the line voltage and the phase voltage for the star connection.